First of all, I would like to thank the Indian Society of Extracorporeal Technology for their kind invitation to give this presentation about goal-directed perfusion. I have no disclosures to make with respect to this presentation. How do we know that blood flow in a given patient meets the metabolic needs of a patient? Well, today we do that mainly by a retrospective analysis of mortality, morbidity, and organ dysfunction in the intensive care unit. Unfortunately, this information comes too late because the insult has already taken place. So what we really need is a multivariate online analysis of risk during cardiopulmonary bypass, which was already proposed in the 1980s of last century by Charles Wildeboer, a well-known Dutch cardiothoracic surgeon. When we look to the oxygen delivery to the body, then we do know that under normal conditions we have about 1 liter of oxygen delivered per square meter per minute. And when this amount of oxygen delivery is reduced, as you can see here, that will be compensated for by a higher extraction from the hemoglobin. So under normal conditions we extract about 25%, but this can go as high as 40%. However, at a certain given point, the oxygen delivery the oxygen consumption, becomes dependent on the oxygen delivery, as you can see here. And this means at that time, part of the energy necessary to maintain life in the body will have to come from the anaerobic metabolism. And that's a region we would like to avoid. Now, important to understand is that in this equation of oxygen delivery, we only have two main parameters, being blood flow and hemoglobin or hematocrit. Also important to understand is that we should not focus only on the systemic values, but we should mainly focus or try to have information about what's happening inside the organs, as it are the organs that fail and not the systemic circulation. And as you can see, there are huge differences depending on the organ. The kidney, for example, is extremely sensitive to a reduction in oxygen delivery. As you can see here, where the linear consumption delivery relationship already starts at a hematocrit of about 30. In opposition, the heart will tolerate very low oxygen delivery and still maintain aerobic metabolism, as you can see, where the critical level is around 10%, and the gut is somewhere in between, around 20%. So that if we look to the microcirculation, the largest organ in a certain way inside our body, then we see that there is a potential for two different limitations. One will be a limitation based on convection. That means that or the native heart or the cardiopulmonary bypass pump is generating insufficient flow. As a result, the red blood cells are not renewed fast enough. And because they are not renewed fast enough, there is a huge extraction from these cells, but nevertheless, at a certain point in time, this will be insufficient and an anaerobic metabolism will exist. Another limitation is a diffusion limitation. And in a diffusion limitation, we might have a normal or even above normal pump function of the heart or the extracorporeal circulation pump, but there are insufficient red blood cells available. So there is a limited transport capacity for oxygen, and as a result, the oxygen which is bound to the hemoglobin has to travel a huge distance in order to reach the cells who depend on this blood vessel for their oxygen supply. And both of them will lead to an increased number of complications and morbidity post-cardiopulmonary bypass. This was acknowledged and brought together in a landmark paper by Marco Ranucci, who said, well, we should not look to hematocrit alone, we should not look to flow alone, but probably we should combine them both and look at DO2. And in his center, where they normally work at 34 degrees Celsius during bypass, he found that the critical hematocrit was about 26% and that the critical oxygen delivery was about 272 milliliters of oxygen per square meter per minute. And what was a very important conclusion was that independent of the hematocrit, just by altering flow, he could reduce the risk for acute renal failure from about 5-6% down to 1-2% just by making the flow dynamic. So goal-directed perfusion wants to be a dynamic perfusion which adapts to the local situation of a given patient. There were several follow-up studies, of which probably the most important one was the GIFT study, which was a prospective randomized international study. But the interesting part is that all of them find exactly the same results, that there is an increased risk of about 2.5 times the control group if you do not maintain a good oxygen delivery during cardiopulmonary bypass. Now, we have learned that it's a combination, and unfortunately this was not always recognized because, as you can see here, there are many meta-analyses and large population studies showing the impact of a low hematocrit during cardiopulmonary bypass on morbidity. And once you actually go around the value of 24-22%, then you will see that there is a huge increase in the morbidity of a given patient. So this was brought together again in a summary by Marco Ranucci, who said that if you want to reduce major morbidity, you saw that you will see the lowest morbidity in patients who already had a good hematocrit to start with, and where the hematocrit remains relatively high during cardiopulmonary bypass. They will have a low morbidity and a low mortality. However, if you have patients referred for the same type of operation, but they already start with a lower hematocrit, and because of that it's not possible to maintain a high hematocrit during bypass, there you will almost triple the morbidity in that patient. So hematocrit during bypass is an important issue. Did we understand that? Because this knowledge dates now for about 10 years, so did we really hear that message? And yes, we did, because here you can see the results of a large population study of 2005, and as you can see there, the average hematocrit was around 23 during the bypass. Clearly shows that we have understood the message, as most patients now have a hematocrit around 30 during bypass, which of course is a huge improvement against the early days. But DO2 alone will be insufficient, because what we are really striving to is to obtain a multivariate analysis, which means that we have to bring in more variables in order to make the statistics more robust. So DO2 would be one variable, but we also know that when we have a DO2 which is insufficient, so we need to switch over to an anaerobic metabolism, that lactate by itself is a very good marker of that. And we do know that we have an increased mortality when we have high lactate levels immediately after the bypass or late after the bypass compared to patients who do not have hyperlactatemia. And also the number of major complications is much higher if you have high lactate levels after cardiopulmonary bypass or during cardiopulmonary bypass. Unfortunately, lactate we can measure it, but we cannot measure it online. That means that we still have a gap of 30 or 40 minutes between two measurements, and in that period of time, we have no clue whether our flow would be sufficient, yes or no. Luckily, we do know that lactate is converted into water and into carbon dioxide, and that we can use in our interest, because we do know that normally the oxygen consumption during cardiopulmonary bypass is about 250 milliliters per minute, and a normal CO2 production is about 200 milliliters of carbon dioxide. That means that the ratio between them is 0.8, and that's what we call the respiratory quotient. So when we see all in a sudden, as you can see here, an increase in the carbon dioxide production, which is much more than the oxygen which is consumed, then we can actually say that this is the start of the anaerobic metabolism. So it's an indicator of the anaerobic threshold. And we do know that carbon dioxide-derived parameters are much more sensitive in measuring anaerobic metabolism compared to oxygen-derived parameters. As you can see here, where we have a very good sensitivity and specificity of carbon dioxide parameters, but we do have a relatively low sensitivity and specificity for oxygen-derived parameters. And Marco Ranucci brought all this back together, and he found out that if you use several of these parameters, that probably the best parameter to detect the anaerobic metabolism was the ratio of the oxygen delivered divided by the carbon dioxide produced, and this indexed to the body surface area of a given patient. And the critical value he obtained was about 5. Now, it's always important to keep in mind that we should have a physiological background. We deliver about 1 liter of oxygen a minute in a normal human being. We produce about 200 milliliters of carbon dioxide, and this brings us exactly to the same parameter of our ratio of 5. And luckily for us, we can measure CO2 very easily, real time, during bypass, as you see here. Now, let's take an example. Here we have a small female. She has a calculated flow with a fixed blood flow of about 2.4 liters per square meter. It would be 3.5 liters per minute. She starts with a relatively low hemoglobin, and it's a combined valve procedure. And as you can see, at the start of bypass, everything is fine. She has an acceptable DO2. She has an acceptable VCO2 because the critical value there would be 60, and the ratio is above 5. It's 6.4. However, this center is using crystalloid cardioplegia. And so here the crystalloid cardioplegia is added. And immediately you see that, of course, because of the dilution, we go from a hemoglobin of 10.7 to 8. You can see that now we have a DO2 which is below the desired target. We have an increase in carbon dioxide, and also the ratio is below 4.2. Luckily, this is happening in a center where the perfusionist is aware of goal-directed perfusion. This perfusion increases his blood flow from 3.6 to 4.2 liters, and as you can see, the result is immediately a return to a normal value for DO2. However, as you can see, it takes much longer for the carbon dioxide to return back to normal. And that makes sense because carbon dioxide is, first of all, much faster than oxygen, and it makes sense that your microcirculation is not recuperating as fast. And we have a whole duration of bypass where we easily maintain all factors and the patient is weaned off. Now, what is the conclusion here? Well, that we had about 10 minutes duration of high risk for this patient. Now, if we would compare it in a center where the perfusionist would not be aware or not willing to use goal-directed perfusion, then you will see that we will maintain at values which are below the trigger all the time, meaning that the patient would be at risk for more than 1 hour. And this is important because we have learned from recent work that it's not only the critical value that counts, but also the time you cannot achieve this critical value. As you can see here, when we have a DO2 of less than 300 in this case, for more than 15 minutes, of less than 15 minutes, this also has a huge impact on the incidence of acute kidney insufficiency. So what about children? Well, children are of course a more difficult group as we have a very heterogeneous group. Children have different temperatures. Many of them are still operated at hypothermia and sometimes even deep hypothermia. But we had luckily the work from a colleague from Paris, Mirella Beaujean, who has done a great job to investigate what could be the critical DO2 for a child and for a neonate. And this was her population, and what she found out was that the critical value is 340, so much higher than for an adult, milliliters of oxygen per square meter per minute. And as you can see here, again, very important, this orange line is the desired DO2 of 340. This would be the temperature in blue, and this is the real DO2 during bypass. In this case, we remain far above the critical level, and we have a very low lactate. Here again, we have a slight hypothermia, but we remain quite high above the critical threshold, and as you can see, we maintain a very low hemoglobin, lactate. Here, however, you can see we are below the critical threshold, and the orange shading gives the time that we were below it. And as you can see, in both situations, we really have an increase of the lactate. In children, we also have the advantage that we can work with not only the cerebral oxygenation, but also with the renal oxygenation. And in normal conditions, the renal oxygenation should always be higher than the cerebral oxygenation. When that's the case, we have a very low, as you can see here, about 1. On the right side, we see a situation where the renal oxygenation is always below the cerebral one, showing that there is insufficient flow in the systemic circulation. And there you can see that there is a serious increase of lactate up to a value of about 7. But why does it not always work? We now already know that we have to use oxygen, being DO2, we have to use carbon dioxide, we have to use the regional oxygen saturation. Well, it doesn't work not always, because what we need is a multivariate online analysis, and that means we need even more variables in order to make this reproducible. And a value which is often discussed but which should not be underestimated is pressure. And pressure is open because what we really need is to maintain in the autologous pressure region. And this you can see here, when there is no change in the pressure, when there is a change in the pressure, but there is no change in the cerebral oxygenation, then it means that we are in the autologous pressure region. And this means that the slope here will be very flat, and then we talk about a Cox index of less than 0.3. However, as we come in a situation where the oxygen saturation in the brain becomes dependent on the pressure, then we have a very steep slope and we have a Cox index of more than 0.3. And it was Mashida Ono who was the first to show that when you maintain within this autologous region, in this patient, as you can see, the Cox index here is below 0.3 in the region of 80-85 millimeters of mercury. And if you can do that for a very long time, remember time is a very important parameter in goal-directed perfusion, then you can maintain a very low major morbidity in those patients. If you cannot maintain it for the most of the time in the autologous region, then you have a serious increase of major morbidity. So we were interested also to see whether we could find a relationship to that. So what we actually did is we looked in a patient when he was stable, this was his normal flow, and then we reduced the flow by 20% or we increased the flow by 20%. And as you can see, when we decrease the flow by 20%, then we see immediately that there is a reduction in the blood pressure and in the cerebral oxygenation. And what we normally would do when you would see that clinically, you would actually give some vasopressor. And this is done here with phenylephrine, and you can see there is an immediate increase in pressure to normal values, but there is even a further decrease in oxygenation of the tissue. So it's important to maintain the idea that both of them have some importance. But what is the most important one? Well, if we go to this 20% decrease, then we also have a DO2 which is below this critical threshold. And that means that we can conclude that the first parameter to look for is flow. The second one, although not unimportant, will be pressure. So to conclude, GDP should be based upon oxygen delivery and carbon dioxide production, and the latter is really important to detect anaerobic metabolism. If we have an increased respiratory quotient, this is a sign of a disturbed microcirculation. We should keep the mean arterial pressure in the autologous region of the patient, and flow is for sure more important than pressure. GDP will reduce the post-operative morbidity. It is a multivariate online analysis of risk, but we certainly need more variables in order to make it even more robust. So, to finally say, GDP wants to preserve organ function by influencing host response, but this asks for continuous markers. Thank you so much for your attention.